So you had a chance to do 6D on your own. Let me do it like a typical student who is fervently excited about the math and just can't restrain the enthusiasm and the effulgent energy that emanates from their math hand. Okay? Oh, find the derivative with respect to m. Okay, all right. So that's going to be 6. I'm going to bring the whole quantity to the top and make it positive squared. That's 6 then times 3 squared times m squared. Let's see, that's 9 times 6, and I can do my little 1, 2, 3, 4, 5. That's 54 on my fingers. M squared. Boom! Kawasaki! That's like answer choice A on the test. Is that right? It's not right. Yeah. What did I not do ever? I never took the derivative, which means I never busted out the calculus. BOTC. Okay? You got to bust out the good stuff, right? And you know why we didn't bust out the calculus? What did I not do from the first line to the second?
You didn't write D over D.
Exactly. I lost a point from my notation, and I never recovered to even try to earn a point for actually doing the math. Right, multiple choice. But if you never practice the formal, part of it, you're not going to be able to step it up. You can always step it down, right? It's hard to step it up. Yeah. So now, peanut butter, what do? Multiply and subtract. So 108, m to the first. And that is when we can then not write the DDM. Okay? Got it? Got it. Yes, ma'am. I took it down to put the pictures up, but I need to put it back up there. We need a BOTC sign in here. I kind of redecorated a little bit at the end of last year.
Yeah, I think you de-decorated.
Yes, I try to declutter. Cluttered? Okay. I'll start bringing the clutter back, because right now it's cluttering up my house and my office.
His wife said you should.
Yeah. Okay. Let's go ahead and expand this power rule to bigger and better problems. 2 quick rules that work with the derivative. First of all, the derivative of a sum is the sum of the derivatives. Works with difference as well. So what that means is if you have multiple terms, you could focus on each term as being their own separate problem, take the derivative of each term, and then just string them together appropriately with the correct sign between them. That's nice, because that makes molehills out of mountains, and that's what we're into doing, right? The next one is the constant rule, and just like with the limit, if you have the derivative of a constant times a function, you can pull the constant out front, take the derivative of the function, and then multiply the result times the constant, okay? But the first one is really, really a nice one, because you can handle now polynomials with many terms, such as example 7a. Find the derivative of the following functions. Okay, so now we're back to the noun format. Instead of d dx, it's like, here's a function, f of x, find the derivative function. So the first step is to realize what we have as our function. It is a 3-term dude, and so we can take the derivative of each term separately. Do any of them need to be rewritten prior to our differentiation? No, they're all good to go, right? Crunchwrap Supreme, good to go. So on the left side, don't forget the left side. What's the derivative of little f? Little f prime, good. Lil, right? You can spell it like this, which is the correct way to show an absence of letters, which I guess you'd have to put one back there too. Or you could do it like this, right? Or like this, right? Anyway, Lil. All right, now, what becomes of x cubed? 3x squared, good. And then mosey over to the next term. Maybe you're already there, because it's not too far away. Negative 4x becomes? Negative 4. Yeah, now that one, let's see that one in kind of a slow motion. If you want to put the exponent there to see what the power rule looks like, there's a 1 implied. 1 times negative 4 is, of course, negative 4. And then we get x to the what after that? 0. Anything to the 0 power is 1. So that's one way to look at it. But if you think about it graphically as well, that term is negative 4x. So if you were just to graph that term and that term alone, it would graph as a what? A line. And what do we know about the slope of a line? It is a constant, right? So it's mx plus b. So the slope of a negative 4x is constantly a negative 4. And then what would be the derivative of 5? 0. Good. Because if you want to think about it algebraically, it's like 5x to the 0 right now. Of course, 0 times 5 is 0, x to the negative first. So that's one way to look at it. Or if you think about it graphically, what would the graph of y equals 5 look like? It would be a horizontal line, right? And what's the slope of a horizontal line anywhere and everywhere? 0. Yeah, so the answer is just 3x squared minus 4. So linear terms go to their coefficient and constant terms go to 0. In fact, I think we had a rule that was called the constant with k rule, right? Yes, okay, good. Letter B. 3 terms. Any rewriting needed? Yeah, maybe the first term, but you could probably do it without rewriting it, but it's early, so I don't want to take anything for granted. So I'll go ahead and rewrite that. And notice as I'm rewriting it, what am I still calling my function? G of x. And what did I do with the last 2 terms? Did I take their derivative? Not yet. Here's what I've seen. Believe it or not, I've seen this. In 18 years, I've seen this. G of x equals negative 1/2 x to the 4th, and then that's like 6x squared, and that's minus 5. Duh! Yeah, that is way wrong. I don't know what that is, but you're taking the derivative of the last 2 terms, not the first term, and you're still calling it G? Well, maybe if you call that G almost prime. I like that. Way to go, Peter. G almost prime. G definitely wrong, but G almost prime. All right. So, hey, you know what? I've rewritten it. I'm feeling kind of exhausted, maybe kind of glistening a little bit for my effort. I'm going to box it and say I'm done. Do we stop when we're tired? No, we persevere. We actually need to answer the question. We haven't BOTC'd yet, have we? No. It's time to BOTC. So the left side becomes G prime. And what does the first term now become? Negative 2x to the 3rd. Next term? Yeah. And we're done. Now, just so that you appreciate the power rule and take nothing for granted, here is another way you can do it, right? The limit as h goes to 0 of negative x plus h to the 4th, over 2, plus 2 times x plus h cubed minus 5 times x plus h. All of that minus a negative, which would be plus x to the 4th halves, minus 2x cubed, plus 5x, all over what? H. And then guess what we get to do? This would be the sledgehammer method, but you know what? This is like hard to expand. I would call this the like jackhammer method, not the sledgehammer. Right? You own a sledgehammer. You've got to rent a jackhammer. Okay? So anyway, if you expanded all of that out and combined like terms and canceled anything that didn't have an h and factor an h out and then divide out the h and plug in a 0 for every h that's left, you would end up with this right here. And that's exactly how the power rule came into existence. It was done with the limit definition using variables for an nth power function. So it's the distillation of this process. It's not just a magic formula that fell out of the sky in France. All right, it was actually developed, discovered, if you will, by living people. All right, letter C. 1 minute. You take a minute. Size it up. Proceed if you can. I'm gonna do the same because I don't know how to do this one. All right. Yeah. So let's just take our own time, and we'll meet back here in a minute. What's that? Oh, if you bring it to the top, you can multiply it in, but if you bring it to the top, you could have parentheses around all that. Okay, then you could maybe distribute it. Yeah. All right, so we're back together. Here's what I came up with. I see that there's a really nice four-term polynomial on the top, and everything's ready to go. And the bottom, I just call that 2x to the 1/2 in my head. So took the derivative of the left side and got dy dx because I like Leibniz notation. And on the top, just boom, boom, boom down the line. And the bottom, there's just one and done. And then I drew a picture of Pigpen from Charlie Brown getting ready for the school dance. Is that right? No, Pigpen always has a cloud of dust around him. So that can't be Pigpen. What's wrong with the calculus part, though? I didn't show anything. Do I need to? Wait, did we ever have a rule that said if y equals f of x divided by g of x, then y prime is just f prime over g prime? Did we learn that rule? No, I don't think we learned that rule. And the denominator is not just a constant, so guess what? You can't do that. In fact, y prime is not equal to f prime over g prime. Good news is there will be a rule later on for that. Right now, that's not it. So what we have to do instead is just get rid of all that. Sorry, Pigpen. We need to be able to write those four terms as a single term apiece, each of the form ax to the n. So there's two ways you could do that. You can either bring the 1/2 out front of the whole thing from the denominator and bring the x to the 1/2 to the top and distribute, but that's a lot of record keeping. You have to be very, very careful with your parentheses and grouping. So what I think is just easier is to split up the terms by putting each term in the numerator over the entire denominator. So we end up with 2x to the third all over 2x to the 1/2, and then rewrite the denominator as 2x to the 1/2, minus 3x squared over 2x to the 1/2, plus 7x over 2x to the 1/2 power, and then plus 5 over 2x to the 1/2 power. Pretty common strategy all year long, and I think that's easier than bringing it to the top and distributing, splitting up the terms in the numerator. Now notice I still called it y, and I am on the next line as well. Now I'm cleaning it up. The 2's divide out, and I'm left with x to the what? The rule says to subtract, right, when you're dividing. So 3 minus 1/2 is 5/2. Good. 3 is the same as 6/2. Minus, we have a 3/2 coefficient. X to the 2 minus 1/2 is 3/2. Plus 7/2 coefficient. X to the 1 minus 1/2 is 1/2. And then finally, plus 5/2, you either think it's x to the 0 in the top and subtract, or you just slide it to the top and call it x to the negative 1/2. Now, this is the point where some people do feel exhausted. They're sweating. They feel like they have captured the essence of the problem. They knew what the trick was, and they stop, right? But again, what have we not done? We haven't busted out the calculus, okay? So now let's do that. We are ready. We have four terms, and they're all of the form ax to the n. So now on the left side, you put y prime or dy dx, and here we go. What's the first term become? 5/2, good, is your new coefficient, times x to the what? 3/2. Minus, do it again. 3/2 times 3/2 is 9/4. X to the what? 3/2 minus 1 is 1/2. And then the next term plus, we get 7/4 x to the what? Negative 1/2. And then finally, minus 5/4 x to the negative 3/2. Now, putting that back into the original format, like a single term, that could be done any number of ways. So you might be content at this point to stop there, which would be fine because you've done the problem now. But I want to go ahead and introduce to you something we'll be doing later on. We'll do it right here. We can factor out common factors, right? We've been doing that quite a bit. But we're typically only experienced with factoring out common factors that are whole positive integers. We could factor out parts that are fractions as well. So let's go ahead and do that. What's that? Well, we can always take out what they have in common, so it would have to be like the smallest representative. So let's look at the numbers. Can we factor out a 1/2 or a 1/4? Yeah, 1/4 is smaller than a half, so factor out a fourth. And then we have pieces of x's in all of them, don't we? So which of those exponents is the smallest? X to the negative 3/2. So we're not looking for just magnitude, we're actually looking for numerical size. Okay, cardinality. All right, so I'm going to factor out a 1/4 x to the negative 3/4, or 3/2, sorry, from every single term. Now remember, when you factor out, you're dividing out, yes? So let's start with the number. And these are stacked right here, so this is beautiful. Look at this. What we did is we just divided 5/2 divided by a fourth on the first term. So say change flip, you end up with 10, right? Now I'm going to get rid of that division bar. But you can really quickly check, multiply the 1/4 back in by 10, you get 10/4, which is 5/2. Here's the next thing, the x's. When you, again, we're dividing x to the 3/2 divided by x to the negative 3/2. What do you do with the exponents? You subtract, right? So what is 3/2 minus negative 3/2? 6/2, which simplifies to what? 3. Yes. Okay, now those first terms lined up, so we got to see kind of like the vertical division. But from now on, we're just going to kind of do it in our head, all right? So the next term, we're going to have 9/4 divided by 1/4. Stay, change, flip, you get minus 9. And we have x to the 1/2 minus negative 3/2 is 4/2 or 2. Good. And then the next one, we get plus 7/4 divided by 1/4 is 7. And then we get x to the negative 1/2 minus negative 3/2 becomes 1. And then I lost track here where I'm at. Sorry, I looked away. There's so much going on here. I looked away. We're on minus. Okay, so we're on minus 5/4 divided by 1/4 is minus 5. And then, of course, when you factor anything out of itself, you're left with just the 1. So we're left with 5 times 1. And if you wanted, you could distribute that back through and see if it works. Now, this is kind of cool because notice everything that's left on the inside is just a nice polynomial. And when you use the power rule, because you subtract 1 every time and you factor out the least powers, it should end up like that. But look now how quickly we can put it back into the original format. I'm going to build my shelf here. And in the numerator is a 10x cubed minus 9x squared plus 7x minus 5. The 1/4 can put the 4 in the bottom, and then the x can go back to the bottom under the square root and then call that x cubed. So that's the quickest and most effective way to put it back into the original format, factoring out least powers. Fractions. So that's a really good problem. I like that one there for a multiple choice type question. Yeah. This is why we worked with fractions a lot in pre-calc. Yes? Okay, that's a good question. The first term that we did, when we factor something out, we're dividing it out. So when we factored out the 1/4 x to the negative 3/2 from the first term, it's like we have this. It's almost like we have this. Oh! That failed. Okay. Yeah. We had this divided by this. Okay, so if you work on the numbers, that's stay, change, flip, right? But look what we actually have. We have x to the 3/2 divided by x to the negative 3/2. So the rule says you subtract. So the new exponent is going to be 3/2 minus negative 3/2. So it's basically the exponent you started with minus the one you factored out. And if we do that all the way through, what is 1/2 minus negative 3/2 or plus 3/2? 1/2 plus 3/2 is 4/2, and that gives us the 2 right here. Okay, and then we'll just do one more time. The next term is negative 1/2. What's negative 1/2 plus 3/2? Well, it's 2/2. 2/2 is 1. So again, it's the exponent we start with minus the exponent we factored out because we're really dividing. Yeah, and we'll practice that some more. That's just good stuff. Yes? Did I mess up on the end? Oh, it could be either way. If you do 4 square root of x and then you cube it, that's fine. Either way, we're not going to be allowed to have negatives under the radical. I'm sorry? Should it be the cube root of x squared? It's x to the negative 3 halves. So remember, the denominator of your exponent is the root, because that's where roots are found underground, in the denominator of the earth. And so the 2 is the root, and so yes, that would be the square root. Yeah, when we take it to the bottom or whatever, remember we just change the sign, so it's x to the positive 3 halves in the bottom, not 2/3. We don't flip it. Yeah, okay, I see that. Good question. There is a lot going on in this problem, and this is why we work so hard in pre-cal to get comfortable working with exponents, because the power rule requires it. All right, so simplify early and often. On that one, we had to split up the terms in order to use it. How about this one here? We got y equals x times the quantity 3x plus 2 squared. There will be a way to take the derivative of this in the future as it sits. But right now, it sits as a product of two functions, and this is a composite function on the second factor. You have not just x squared, you have blob squared. So this would be later requiring two different rules. But right now, the only tool we have is a hammer, and so we have to force everything that we want to work with to look like a nail. And right now, that doesn't look like a nail. So what do we need to do? Yeah, foil, expand it out, right? Sledgehammer. So you want to try and do it all in one step? Yeah. Since we're BC? All right, so we're going to square, multiply, double square. And then we're going to distribute an x to every term, which means we're just going to add 1 to the exponent. You did it in 2 steps. Okay, put equals down, because now you went from an equation to an expression. There we go. All right, so square the first, you get 9x squared. 3x times 3x is 9x squared. And then it becomes 9x cubed. Oh, there it's lagging a little bit. And then I multiply to get 6x. I double that to get 12x. But then I add 1 to get x squared. And then finally, I square the last and get 4. But I distribute the x and I get 4x. So if you need to do that in multiple steps, that's fine. Just remember that when you're squaring quantities like 3x, you got to square each factor. Just remember you're telling yourself it's just 3x times 3x. Now, you wouldn't be asked to expand anything like this probably greater than degree 3. Degree 3 would be probably the highest. Degree 4 and above is just, it's too tedious. That's kind of like for an algebra 2 class or something, college algebra. So now that we have it expanded, are we ready to differentiate? Yeah, so the derivative of the left, I'm going to use dy dx this time. And on the right, I get 27x squared plus 24x plus 4. And there you go, instantaneous rate of change equation. I can find the instantaneous y value at any x by plugging it into the top, and now I can plug that same x value in there and tell you how fast that y value is changing at that instant. That is so beautiful. The power rule. Powerful rule. That's it. That's all we have to do on that one. So simplify early and often. All right, the next one. It says a powerful application of the derivative is finding the x values where the function has a horizontal tangent. So I told you that y equals f prime of x is a formula. And if you know the x, you could plug it in and find the slopes there. But if you know what your slope needs to be, you could set it equal to that number and actually solve for x. And finding where a graph has a horizontal tangent is going to be of paramount importance. Because think about it. What does the slope of the horizontal tangent line give us? 0, yeah? And let's say you have a function that looks like this, and let's say you have units produced for some business model, and then you have profit on this line, and you're measuring it in dollars. You might be interested in what the optimal production level is to maximize your profit, yeah? So if you can somehow write an equation that models that based upon, empirical data, you can collect data and do like a regression curve, then you can use that data to help you decide where you want to be at production. So obviously we want to be up here, right? So notice, what is the slope of the tangent line there? 0. And you're going to pick up these other local mins and local maxes, but if you could take the derivative, f prime, which would be measured, by the way, in dollars per unit, and you set it equal to 0, you can then find those critical values of production, is what we're going to call them, critical values. So that's the power, one of the powerful things about calculus is allowing you to optimize. And there's a whole section on optimization later in the year. And like every other topic we study, it's a lot of fun. No one laughed. You know why? Because I was serious. And so are you. All right, so let's go ahead and do that. It says find the coordinates x comma y and the equations of any horizontal tangent lines to the curve y equals that. All right, so that's a fourth degree polynomial with a positive leading coefficient. So the graph might look something like a W, like that, maybe, okay? But I want to know where they have horizontal tangent lines. So if you remember from like Algebra 2/Pre-Cal, a degree 4 polynomial can have at most n minus 1, in this case 3 local extrema. And I think we know exactly why now, because what do I do when I take the derivative? Y prime, what becomes of x to the fourth? 4x cubed. If by very definition the derivative is 1 degree smaller, you're going to have one fewer possible solutions to the equation y prime equals 0. Minus 4x plus what at the end? 0, okay? So now rather than just plug in random values for x and find the slope there, I can now set it equal to 0. And now I have a conditional equation that I'm trying to solve. First rule of factoring is to factor out a common factor. So it leaves us x squared minus 1. And when we solve, we get x equals 0, x equals negative 1, or x equals positive 1. Now I know exactly, based upon just the nature of the polynomial, which way it opens. This one over here has to be x equals negative 1. This one has to be x equals 0. This one has to be x equals positive 1. So I know that basically this first value is a local min, the second one's a local max, and the other one's a local min. Now we're not going to have time to finish this because we need the y values there, but it's real easy to finish. All you have to do is plug these x values back in up here. And what's the equation of a horizontal line? It's just y equals the y value. Yeah. So like at 0, it's going to be y equals 2. All right, have a great day. I'll be chipping away at that worksheet. It looks like we should finish tomorrow, fingers crossed. So we're looking like a Thursday due date for the worksheet. Worst bowl.